All right, in this video we'd like to look at closed tubes again. Normally this would be a lot easier because I could just show you some demonstrations. But what we have here, and this is what I would do in class, I'd have a graduated cylinder kind of full of water, and I have another open tube that didn't have anything in it, and I could put it down into the water, and so basically I can change the length of this column of air up here. Now on this end it's open, but on this end the water right here would actually clamp it off. So this would be this column of air would be called a closed tube. Even though it's open on one end, it's closed on the other. And I could hit a tuning fork and put tuning fork sound waves down through it. And if the tuning fork, the natural frequency of the tuning fork matched the natural frequency of the column of air, then it'll amplify the tuning fork sound. And I had a video on the playlist of that one kind of crazy scientist guy demonstrating that would all of a sudden be really, really loud if you had the exact column of air that matched the same natural frequency as the tuning fork. And so that's what we're using when we're trying to vibrate a certain column of air, how we're doing that. Okay, so if we have a column of air, if you remember from the last video, that there's the most natural mode of oscillation would have to be a node on the end, and it can be open loops on the top, an antinode on the top. So it kind of looked like a V. So this would be, going back and forth. This would be a trough here, but it'd go up here to a crest, and then back and forth over here. But down here there'd be a node the entire time. Be a node right there. Okay, so that's the most fundamental way it can vibrate. Now, if you look at that, what we want to do is we want to kind of figure out the wavelength, because we can use this to figure out the velocity of sound in air. It's interesting. Velocity is frequency or wavelength times frequency. And so if I know the frequency because I'm going to use a certain tuning fork right here. I'll know that frequency of that tuning fork, right? And all I have to do is multiply by the wavelength of the sound, and I would actually have the velocity of the sound in air. This is a way we can actually measure the speed of sound. Well, how do I get the wavelength? Well, I know the column of air that I'm vibrating. I know how long it is. I can actually measure from right here up to here. I can measure what the length of it is. So how can I figure out what the wavelength is, though? Well, if you look in here, this is how much of a wavelength. This fundamental frequency would be a quarter of a wavelength, So to find the wavelength, all I have to do is take 4 times the length of the tube. So the wavelength should be 4 times the length of the tube. 4 times the length of the tube. Okay, so that's our basic equation to figure out how, if I'm putting a tuning fork over a closed tube, I make the tube as long as I need so I hear a really good loud sound, and then I know that I'm vibrating this column of air at its fundamental, which looks like this. So all I need to do is take 4 times the length of that particular tube. But the question might come up with, doesn't it matter on what the diameter of this tube is? And yes, the diameter would affect it a little bit. So if you look in your books on page 83, there's a kind of a slight adjustment for the diameter. So you get the wavelength is 4 times, but you're gonna, before you multiply 4 times the length, you're gonna take the length and you're gonna add on 0.4 times the diameter. So get the diameter of the tube, take it times 0.4, and add that onto the length. That kind of basically it changes the effective length of it a little bit. It adjusts the length a little bit. And you can take that times 4, and you'll have the wavelength of the sound. Now, sometimes in the problems, I might say, just ignore the diameter. Just don't worry about the diameter. And basically, to get the wavelength, then you always take 4 times the length of the tube. This is only for closed tubes. Now, watch. Again, I mentioned this earlier, but if I were to double the frequency of this, that would be the second harmonic. I could not actually get that column of air to resonate with a tuning fork that had twice the frequency as that fundamental. Because to do that, it would have to, this right now, this is the fundamental. It would have to double that, and it would have to go like this, and it'd have to be closed, and it can't be closed on that open end. So what can it do? Well, it can do this and then open back up. It could do that, right? So the fundamental is like this, right? But this could be 1, 2, 3. Okay, so this is the fundamental. This is the third harmonic, and it could vibrate at a third harmonic. It could not vibrate at a fourth harmonic. Sorry, second harmonic. It can't vibrate at a fourth harmonic, so it would have to close back up. But it could go like this. It could vibrate at a fifth harmonic. 1, 2, 3, 4, 5. Right? I'll show that with an arrow. It'd go 1, 2, 3, 4, 5. That'd be a fifth harmonic, and it could vibrate at that. So for closed tubes, you only get odd. You can only get the odd harmonics because you can only force the column of air to vibrate at the odd harmonics. That's the only way you can do it. And the reason is because you always have a node on one end and an antinode on the other. It's kind of called the law of odd nodes. Okay, so you can only get odd harmonics with closed tubes. And here is your equation you're using for the ELAB and the JEDI trial for calculating the wavelength. If you might want to find the velocity, you need to take the frequency of the tuning fork times the wavelength of the tube. And the way you find the wavelength of the tube is you use this equation right here. If the diameter is negligible, you don't have to worry about it. You just take the 4 times the length of the tube. That was a long video just to explain some actually fairly simple math.